2 or 3 weeks ago, but I got sick, so now that's why I'm giving 2 talks at this conference. So one is, so, yeah.
Well, this is,
right.
you know,
Well, it might be actually appropriate.
It's very good. Right. Not good that you have
right.
sick,
yeah, right.
Very good that you
right. Very good. Okay, so let me start with my viewpoint on what this business of geometric universality is. It's geometers doing computer science. That's what it really is. So we are trying to build some kind of machines of geometric nature to do computations. So it's really so geometric universality is building geometric machines to do computations. And some of these geometric machines, computer scientists, or well, engineers, would really recognize as computers. They recognize them as analog computers. And this is what computers were until 1940s, maybe until 1950s. Computers, you can see some of them in this Arithmeum, this museum. You can see these computers built out of steel and, you know, some other, mostly steel. Maybe wood, I don't know what else they use, but definitely there were nothing about this, you know, logical gates or anything. They were really kind of, and again, what you will see in this talk are kind of, really something which really looks like an analog computer. But some of the geometric gadgets are further removed from analog computers, and the engineers, at least the sane engineers, will never accept stable sheaves as analog computers. You know, even though some of them might know what a sheaf is, but they will never accept that this is a computer. Okay. So, and what computations is, again, I will also illustrate several key ideas. What computation? It's primarily arithmetic computations, addition and multiplication.
So you consider digital computers, not computer in the sense of 40s.
Yeah, actually, that's okay. So there are modern computers which are almost never analog computers, as far as I can tell. But this stuff is really analog computers in some form, except that some of them really look very, very far removed from, right? Well, no, I'm not doing quantum computers. So, right, so computations are mostly the arithmetic computations, addition and multiplication, okay. Subtraction and inversion. Again, once you understand how to do addition and multiplication, you can figure out the, you know, the 2 other operations. But also, I will, if I have time, I will talk about one more operation, namely differentiation. Okay, so and that's what engineers analyzed a long time ago. That one can use analog computers to solve differential equations, to encode the differentiation, and I will maybe illustrate some of this in the talk. Okay. So typically how it goes is that there is some kind of an initial encoding. Again, I will mostly talk about just arithmetic operations. There is an initial encoding, and there are really only 2 ideas for this initial encoding as far as I can tell. So there's an initial encoding. And again, as far as I can tell, there are really 2 radically different, although I will explain how to relate them, ideas. One is due to von Staudt, and it's around 1850. He published a book, at least around. When he came up with this idea, I don't know, presumably before he published the books. It takes some time to publish the book even in those days. And the second idea is due to Kempe. It's, at least the paper was published in 1875. And it's clear that the paper was conceived shortly before that. So we can actually, there's a very narrow window when he came up with this idea. It's between 74 and 75. And I will explain why. Okay. There are really 2 ideas and they're related. So Kempe's idea is really like analog computer. Where he does computation over reals. So the computations with real numbers, and moreover, again, the von Staudt is also over real numbers, if you like, but his constants have to be, say, rational numbers. while Kempe's construction is really the only one which can encode real constants in the equations that we're going to describe. Okay. So this is really, and von Staudt is secretly over Q, or if you like, it's, again, in some sense, they're incompatible. So you cannot say one is more powerful than the other, because von Staudt really works over arbitrary commutative rings. So, and then Q would be an example, or Z would be example. And then coefficients will be whatever primary ring you have. For example, it could be, say, finite field, and then the primary field will be coefficients. Or maybe Q, and then coefficients are in Q. Okay? While Kempe really works over real numbers. Okay, secretly over complex numbers. Okay? Up to very last step, all computations are over complex numbers, and then you make things real. Okay? But again, the advantage here, you can encode real constants as well as analog computers are supposed to be, because digital computers really cannot handle real numbers, to be honest, right? Again, one can kind of fake it, but again, in reality, they're designed not for real numbers. Well, analog computers are, at least in theory, supposed to be able to handle real numbers as well as rational numbers. Okay, so let me start by describing the von Staudt's construction, which I learned from Anatoly Vershik about. It was 1989 when he gave a talk at Lake Baikal that found absolutely amazing about Mnyov's theorem, and I used ever since this von Staudt's idea. So let me describe this. So along the way, I will describe what kind of a geometric object. So far, I was very vague as far as saying what geometric objects are. I was saying what, coherent shift, I mean, stable shifts, but I'm not going to deal with stable shifts. My geometric objects will be really geometric. Okay, they're geometric in the sense of 19th century geometry. Okay, so let's start with von Staudt. So our basic object is a sort of abstract projective arrangement. So abstract planar projective arrangement, which I will call A. And if you think about this, well, what's a projective geometry? Well, there are lines and points, right? So this abstract arrangement will be bipartite graph. Some nodes will be called points, some nodes will be called lines, okay? And edges between them is the incidence relation. This point lies on this line. So it's just a bipartite. Again, all my graphs will be finite, so I will not even say so. Finite bipartite graph. With vertices labeled points and vertices labeled lines, and then some edges between them, which encode the incidence relation. That's an abstract arrangement. And again, of course, one can also talk about more general abstract arrangements where we'll have planes and so on, but here I just will stick to points and lines, because that's enough for us. Again, all the complexity is here already. Okay, and then I will talk about the space of realizations, R of A. Space of realizations of A in P2. And I'm intentionally vague about P2 over what? P2 over whatever you like. You like real numbers, real numbers. You like rational numbers over rational numbers. Complex numbers, complex numbers. If you like some weird, if you like sort of Z, it's over Z, whatever again. Plug in anything you want, okay? Finite field is absolutely fine. Again, I'm curious if there is any way to make sense of all the stuff over some kind of other things like Boolean algebra, God knows what. I don't know. But for me, this are really, maybe. Quaternions, maybe. But again, for the purpose of this talk, everything is commutative. Okay. Again, there is enough complexity here to, Again, occasionally people ask me, I don't know. I never spend enough time thinking about non-commutative algebra. Okay, so realization in P2, so what is this? So it's really space of maps, F, from A. And again, A, remember, really for me, A is a set of vertices. It's a set of vertices in A. Vertices in A into P2 union P2 dual. preserving incidence relation. Of course, well, P2, so vertices called points go to P2, vertices called lines go to the dual P2, right? So points become points and lines become lines. And preserving incidence means that if this point is incident to this line, well, this F supposed to send, you know, this point to point on the line. No, vice versa, I don't care. It might not be faithful. It might be that, you know, maybe this point is not incident to this line, but under realization they become incident. That I don't care about. It's like a homomorphism, doesn't have to be injective. Okay. So this space of realizations. Now, if you think about this, you realize that really it's a variety, right? It's a projective variety, and moreover, it's a scheme. If you don't know what schemes are, just ignore this. This is just a word. Just think about a set of, you know, again, just plug in your favorite field or a ring or whatever, and think about just a set. That's good enough. But it's really a scheme. So it's a scheme over the integers. Because again, if you once you encode this incidence into, you have to do it in terms of over real cell, in terms of linear algebra in three-dimensional space, right? But then you can encode this over for arbitrary rings. You have to use three-dimensional models over rings and so on. Then you realize that you are just doing, you know, everything is over integers. Okay. So that's a scheme over. But again, you just can think about this just plugging in a field and think of this as a space. Okay. The space of realizations, and then one can also form the quotient, the moduli space. M of A is R of A. Modulo PGL 3. And okay, so if you have a projective transformation, of course, it preserves all the incidence relations, right? So if you, again, applying projective transformation doesn't really change realization too much. This double bar means you have to make a smart quotient. And I will not talk about how you make quotients. Again, at some point it will come up, but again, I will spend otherwise the rest of my talk just talking about Mumford quotients. There is a way to make quotients so that the quotient is again a scheme over Z. So this is algebra geometric quotient. It's not the naive set theoretic quotient. One has to be careful with these things. So it's again scheme over Z. Okay, scheme of finite type. Again, my schemes are finite type. Again, think about just sort of giant projective space, or maybe a finite space above it, and just finite dimensional one, and just set of polynomial equations, homogeneous polynomial equations. Okay, so it's a scheme over Z of finite type. But again, just think of the just a solution set of some system of polynomial equations. Finitely many variables, finitely many equations. Okay. And so what von Staudt realized is that this is absolutely powerful. So this will be our computer. So this is our computer. This arrangement. So it's as powerful as a kind of a digital computer in a way, because it's, again, in the end of the day, it's kind of everything is over integers, over rational numbers. That's why it's sort of more like a digital computer. Okay, so again, what he realized is you can encode basic algebraic operations. He was thinking about over real numbers or complex numbers, but it really works over arbitrary rings. You can encode algebraic operations and therefore systems of equations using such computers. So let me explain what are the basic machines that he devised. Okay. So the basic machines. Again, of course, if you want to encode addition and multiplication, and then of course you also have to encode how to compose them, but the main thing is just the addition and multiplication. So here is the addition. So I'm drawing the x and y axis in the plane. And then there is, of course, secretly there is a line at infinity because it's a projective plane, right? Here it's, again, I'm doing some kind of a violence to this problem because I introduced the coordinate system. But that's what this Mumford quotient allows you to do. It allows you to secretly introduce coordinate system into this problem, which is, on the face of it, it's not there, okay? And then, moreover, I have point called 1, 0, and I have point called 0, 1. Again, this is the Mumford quotient business. And so this is my basis. It's like introducing a basis in a vector space, if you like. The system of lines and few points. In particular, it allows me to define diagonal, right? Because I have, there's also diagonal here. So there's also a point called 1, 1. Again, for example, So for example, how can we define this point? We just have to draw a line, kind of a vertical line through this point. Vertical means it's incident to this point. Again, there is a secretly also, there is a couple of points at infinity here. Okay, and then you draw this one, you define this point, and then you draw a line incident through them. So that's how you define the basic coordinate lines and maybe diagonal line. Okay, now we'll do the algebraic operation. So the addition. So again, I will of course draw things so that they make sense in the affine plane rather than projective space, but it should. But being parallel is, it's the projective notion. So you have a point called, I just will call it A, but it's really A comma 0. Okay. So you draw A, you draw a line through A and the point called 1, 1. Okay. Then you take a point B and draw a vertical line through it. And again, vertical line around means that's incident to this point at infinity, right? You find a point of intersection here. Okay, I'm running out of room. This is my x-axis. And now I have to draw a line through this point, which is parallel to this one. And then you hit a point here called C. And then what from out observed is that C is equal to A plus B. Again, over reals, it just takes, well, very, very little time to convince yourself that it really works. What we verified with John Nielsen is the same works over arbitrary commutative ring. So it's not just an accident of Euclidean geometry. So this is the machine for the addition, okay? So the inputs will be these two nodes. Again, secretly, these are vertices, right?
What is A capital?
Oh boy, so again, there will be probably 20 vertices of various kind. Again, you can see some of them, right? This guy is a vertex. Maybe this. I mean, okay, so I'm drawing the picture of already realization, but then you can go back and kind of, again, in our paper with Nielsen, we kind of carefully kind of drew graphs, but it's...
Yeah. Another small a, you need another capital A. So your capital A solves only this question.
Yeah, my A is just a graph. Again, you can see, again, this graph with, okay, I can label all the vertices on this graph, but you can see what they are. This. There are sort of few of them with infinity.
You're trying to describe the triples A, B, C, such that C.
Yeah, well, it's the output of the machine, right? Again, but again, you really have to think in terms of the abstract graph, right? And realizations of this graph. So that, of course, you know, the lines, there are special lines in this graph which go to the coordinate lines. There are few, there is a normalization you have to assign. But then with this normalization, every realization of this arrangement will have the property that if you look at the location of the node called A and node called B, then the location of the node called C will be A plus B. Okay. So that's just, okay, so it has this property. Notice that things go, again, and that relates to Bernd Stock. That's why I was asking him this question. Things go badly. Where? At infinity. This is where things just break down completely. You know, this just becomes complete nonsense, these equations. And we still, again, as far as I know, it's still unclear what, is there any way to fix this? To find some sort of a way to, again, who knows? Maybe it's impossible, maybe just we're not smart enough. Maybe, yeah. Who knows? But again, so this is the addition. And now let me draw a picture for multiplication. So you need the, so this is supposed to be diagonal line. A point called 1. And then we'll have, let me see. So I will draw a vertical line through 1. Then drawing this. So this is my A. There will be a point called B. And there is a vertical line through it. And now I have to draw a line parallel to this one. Again, lines which look parallel are supposed to be parallel, right? Okay, and this is called C. And then you realize that C is equal to A times B. Again, this over reals, it's elementary Euclidean geometry. There is nothing there, okay? But again, it works over arbitrary rings. But you have to make sense of all this stuff over a ring. Okay.
Let me ask you something. Just to keep us on the right say the word computer, I think of conditional operations and loops.
I have no idea what it means. For me, computer is, again, for me, computer is something much more primitive. So it's a kind of computational device where there are inputs, there are outputs. Calculator, right. My computer is really much more primitive than yours. Again, just think about this. So these nodes are called inputs. This is where you input your variables, and this node is output. Again, both of them have the same nature. So there is a machine, there are two inputs called A and B, and there is one output called C, and the same there. And of course, once you have this, then you can combine them, okay? Put them in one after another to make compositions of these operations, okay? And you can also make equations, right? For example, if you encode equation, say, AB equal to 0, how can you do it? Well, you just have to declare that this vertex, labeled C right now in your graph, is the same as this vertex labeled 0 in the graph. You have to identify them. This absolutely forces C to be 0, right? So this forces this equation, okay, on the two input variables. And the same in general, okay? Okay, again, so making it actually work formally, again, what we did with Milson, we made it work over on scheme level, on the level of schemes rather than the level of just real numbers, okay? So it works over arbitrary rings, that's how we did it in the end. That's why it works on the level of schemes, okay? So there it requires more thought, understanding what does it mean to compose these machines, how to translate this into language algebraic geometry. It's called fiber product. And similarly, what does it mean equation? It's also, again, some sort of fiber product, and then things worked in the end, okay? So that's the basic idea, okay? And now you understand how to compose the machines and then how to describe arbitrary systems of equations using this stuff, okay? So then the theorem which came out of this, and again, von Staudt did not state this theorem because he was after something else. But again, this theorem is really in Munyov's paper and in Wybershek's paper from 1980s. But again, if von Staudt knew of the language, he could have easily stated the theorem because he had all the tools for this. Just the language of algebraic geometry really did not exist at the time. So it was, again, just projective geometry was the only geometry he knew about. So theorem. And I will state this on scheme theoretic level, in which case the first proof is by me and Milson, so because we did it over arbitrary rings. That's how one takes care of schemes. So theorem. Says that so let X be an affine scheme over Z. And again, think about finite types. So again, think about just a space, finite dimensional, finitely many variables, and finitely many equations. That's what scheme really is. Equations with integer coefficients. Again, you can also do it with Q coefficients, but it really, just clear denominator. It makes absolutely no difference whether you use integers or rational numbers as your coefficients. There exists A, and A is one of those bipartite graphs. So that, well, what I would like to say is that X is isomorphic to M of A. That's what I'd like to say, and this is false the way I stated this. This is nonsense. Because, again, you realize that M of A is really projective. It's, and this X's are fine. So it's isomorphic to some M naught open here. So there is a subscheme here, which is open, which is isomorphic to this X as a scheme. Okay. So again, if you like, if you don't know about schemes, just think about just plug in real numbers, and they will be isomorphic as sets. There is a polynomial as a map of the ambient space, which will carry one set to another set. And there's an inverse which does the same in the opposite direction. But again, it really works. It will be over rational. Again, it will be over Z, so over Z. Isomorphism over Z. It's isomorphism of schemes over Z. Notice again, this is issue that, again, we would like to say, again, this is the main kind of motto of universality, that whatever is not clearly forbidden is realizable, right? That's what universality is. Again, this stuff is a scheme over Z, so the idea would be that, any scheme over Z should be realized. It almost works like this, but not quite. Okay, the right theorem would be to say, so here's a conjecture, or open problem. So given a projective scheme, let's call it maybe not X, but Y over Z, there exists A, so that M of A, well, Y, is isomorphic as a scheme over Z to moduli space of A. And I have no idea whether it's true or not. If it's false, there are some sort of very kind of interesting abstractions. Because again, this arrangement is extremely powerful. They're as powerful as bipartite graphs, so you can encode all kinds of stuff into them. On the other hand, the non-proofs really break down at infinity, right? Again, if you try to push this A and B to infinity, things just go wrong.
But M of A, you understand this?
Yeah, in the same sense. Okay, you have to. Again, you're free to choose. Again, Mumford quotient is not unique. You need a data called line bundle to define it. Just pick your favorite line bundle. Just use whatever line bundle you like, but form a right quotient. Again, this is in the sense that, again, I'm kind of skipping here construction of the quotient. But again, free to do whatever you like to construct the quotient space, as long as the scheme not some garbage. Okay, and
So just to see if I understand the rules of the game here,
Mm-hmm.
I could set up an arrangement which appears to be talking about two lines meeting in 2 points, and then I get some nilpotence over here, or what happens?
No, to get the first nilpotence, you have to really be. You have to do something more subtle than this. Again, in our paper we actually described the arrangement of the equation x squared equal to 0, and it's complicated. There is already a huge number of points and lines, but two of them is just not enough. It's too rigid, right? Yeah. So no, it's much more complicated. No, it will not help you. No, you need as far as I can know again. No, no, that will not be enough. Okay, again, you need more stuff.
Why you can prove this?
Okay, the answer is this picture. This picture just breaks down when you push A and B to infinity. Again, to talk about projective, all projective realizations, you have to allow A and B and C to be at infinity, right? Or maybe A, say, at infinity. And these equations just break down. They make absolutely no sense. Again, maybe C is actually independent of A and B. If you push, it's like, again, just imagine you divide, it's like dividing by 0, So again, things are just undefined. So C will be maybe independent of A and B if you push things to infinity. Or maybe, let's say better, suppose you have equation of the form 0 times infinity equal to what, right? Imagine that A is at 0. Imagine that B at infinity. What C is going to be? Answer is it's anywhere you want. It's anywhere you want on the real axis. So it becomes independent of A and B. If, say, A is at 0 and B is at infinity. So it's no longer what we call functional arrangement. Functional arrangement is supposed to define a function of, say, 2 variables, maybe more variables than this, but it's just the functionality of this arrangement breaks down.
This is a question of language, it's not about...
No, it's a question, it's not a linguistic question. It's a question of constructing the right device which would work over the entire space of projective realizations, not just this. We call them finite realizations, where there are these input nodes which have to go to finite points which lie in a fine line rather than at infinity. So again, as long as you're having these finite realizations where inputs stay finite, everything works nicely. But the question is how to come up with, because maybe one needs more better basic constructions. Maybe one needs something else, but it's not a linguistic question. It's a real mathematical question, which is unanswered since, since basically Munyov's paper, really.
Just that linguistic in the sense change the tools.
Maybe or maybe not. Maybe you just have to, again, the tools, again, if it's true, if the answer is yes, maybe the tools are kind of the same. You just have to have a smarter arrangements to take care of the infinities. But I just don't know how to do it.
What,
If I knew, I would have written the paper. Sorry?
what if the answer is no? So
Then it would be something very interesting, actually. This would be it would be a kind of a new theorem. Like again, the question is whether universality is good or not. So if you discover abstraction to universality, you might have discovered something very interesting in this sort of geometry, right? It's not impossible. Again, that's why I was asking Bert: does it work on the boundary or not? And I suspect that it's actually unknown. That would be my guess. Again, given the complexity of this whole thing, the answer is what Ruhira Datar did doesn't work, but maybe something else works. We just don't know. We know this doesn't work. Compactification. But again, if you think about this conceptually, again, this object is really projective. It's not affine. It's violence to introduce this affine coordinates. It violates its basic rights. It's unconstitutional, okay, what we are doing here. It's a violence towards this problem. And we are paying the price for introducing these coordinates and whatnot. So again, it's possible that this is just kind of inevitability, that we cannot do better than this. But then it's a deep theorem, because it would be a theorem about absolutely arbitrary arrangements, which are extremely powerful, as you see. You can encode any arithmetic, any polynomial equations with integer coefficients or rational coefficients. Okay, it would be something highly non-trivial, as far as I can tell, if there was an abstraction, and I have no idea what it would be. Okay. So, and again, in all these universality theorems, you see this issue. Things kind of work, but only up to a point, and then they break down. We'll see it again in Kemp's theorem. Okay. So let me. Oh yes, oh yes. It's a different equivalence. It's not a homotopy equivalence. It's really isomorphism of schemes. What is isomorphism of schemes? Well, you can think of these are affine schemes really. So these are ideal. So there is an ideal and there is a quotient ring. So rings are isomorphic. There is no stabilization of any kind here. It's really isomorphism on the nose. Okay, but you have to pay the price, namely a kind of again something is unnatural about this, right? Because one object is clearly projective scheme, the other is not projective. Right? So again, there is a mismatch. Okay. So this theorem, as far as I can tell, was reproven by Laforgue a few years later. And my joke is that even though this paper was published in France, it was published in English, so he did not read it. So, okay. So now let me go to Kemp's theorem. Okay. And again, this is the initial encoding, by the way. So then there are kind of field encodings, and I don't know, I will run out of time soon here. But I will talk maybe tomorrow on how to go to a representation varieties of groups, how to use it for three-dimensional topology, say. And Muñoz and Richter-Gerbert did again, this is secondary encoding, how to go from arrangements to something else. We went to groups. Muñoz and Richter-Gerbert went to polytopes. Again, Muñoz probably will talk, again, I don't know what he will talk about, but it's probably somewhat related to his old work, so you will see some glimpses of this. But again, I just have only so much time. So there is a secondary, there are other extensions. There are extensions due to Muñoz, then Richter-Gerbert, so who also did not come. So again, this is did not answer. Who knows? Maybe he no longer cares about this. These are about realizations of convex polytopes. Muñoz did this in high dimensions. He managed to do it in the lowest dimension possible in dimension 4. And then there are our work with Milson. And then there was further work by Ravi Vakil, who applied this to algebra geometric moduli spaces, but again, there's only so much ground I can cover. I want to cover the basic stuff. So this is kind of a second tier. After you did the initial encoding, you can continue sort of this computer business with field encoding. It's like Gödel's theorem, right? Gödel originally encoded the Turing machines or whatever they were called at the time into equations. And then people did later on the secondary encoding, like encoding into first semi-groups, and then Novikov and Boone into groups, right? So again, once you do this initial round of encoding, you can kind of continue and getting kind of other universality theorems. But again, there is only so much time I have. Okay, so let me switch and talk about the Campus universality. So I hope it was clear. Again, please ask me if, again, the basic stuff is very, very clear here, I hope. By the way, what was, I forgot to say, what was von Staudt's motivation? He did not care, he did not know what algebraic variety is. But what he introduced this in order to prove this fundamental theorem of projective geometry, that if you have a projective transformation of the plane, it just means it preserves the collinearity, right? Then it's really induced by this linear transformation plus automorphism of the field. And the way to do it was through this, right? That's how he did it. And then, of course, that led to all kinds of further developments in the 20th century, like work of Tietz on buildings, where is the outgrowth of this work of von Staudt, and then many other papers by other people. Let's see, Hilbert, I forgot. So what was Hilbert's role in this?
Well, it's 1890, I don't remember, 7, maybe 8. But he constructed the field looking on the projected plane.
I see. Okay, so reconstructing the field, but again, in some sense, it's kind of here, right? But okay, right. He mentions von Staudt, right? Okay. So let me switch to Kempe. But again, we'll keep these arrangements in mind because we'll see a relation to Kempe which is not apparent at first. By the way, these arrangements really look like digital computers in the sense they're just graphs, right? So everything is digital. It's either there is H or there is no H here, right? There is no kind of ambiguity, right? You cannot do, there are no real numbers in this thing. Right? So, but Kempe is like analog computers. Okay, maybe I'll remove them because we don't need the machines. So 1875, he wrote a very nice paper called How to Draw an Algebraic Curve, okay? And what was his motivation? His motivation came just a year or two before. It was this work of Passelier and Lipkin. Basically it was about how to draw a straight line. And he actually, Kempe wrote a paper, follow-up paper entitled How to Draw a Straight Line, describing his version of inversor, a machine which converts circular motion into straight line motion, okay? And then shortly after he realized, well, if I can draw a straight line, I can draw any algebraic curve. Again, he did not quite have the right idea. Again, he had the right idea, but he didn't have the right language to formulate the true theorem behind what he was proving. And again, as you will see, the machines do not quite work. Again, they work up to a point and then they break down. And I think there is a serious issue behind this. Again, we managed to, with Milson, kind of eliminate this breakdown as far as possible, but again, up to a point. So let me state what was his main object. So before we saw graphs, right? But they were kind of just digital graphs. Either there is H or there is no H. Now we introduce weights to this graph. So every way, H will come with the length. So L is a metric graph. Just for us, it's a graph where every H is assigned a positive real number. And again, that's all what you need to know at the moment. So this means that every H is identified with the interval in the real line, okay? It's a metric graph. And then we'll again form a space of realizations, R of L. It's a realization space. And I will assume it's connected to keep things clean. Again, if it's disconnected, again, there are some things which work differently for disconnected graphs, so I will assume it's connected. It's a realization space. So as before, what is this? So it's a space of maps, F from L. Now I will take the whole L, right? Vertices and edges together. Maps into R2, which are isometric on edges. So again, it literally sends every edge to a straight line segment of the same length. And that's what it means. And again, there is also a moduli space, M of L. So it's a space of planar realizations. One can also talk about spatial realizations, but again, all the complexity is already here in the planar case. M of L is R of L divided by, now you have to decide what to divide by. So there is a group of Euclidean rigid motions you clearly want to divide by. You want to divide by translations, that's clear. Then you have to decide whether you want to divide just by rotations or also by orientation reversing isometries. I will only divide by orientation preserving isometry group, isom plus of R2. There is a reason for this, namely that we are keeping ourselves in the category of algebraic varieties, algebraic sets, rather than semi-algebraic ones. Again, if you allow reflections, you get only, in general, semi-algebraic sets, semi-algebraic varieties as the result. So that's why I'm dividing by only orientation preserving isometries. Okay, and again, it's clear how these isometries act, right? You just kind of rotate to translate the kind of this Euclidean motions. But again, you have to. These are orientation preserving ones. Okay. Again, so in particular, for free, typically I will have an involution, M of L to M of L involution. So immediately you see that there is a restriction here, right? Again, apart from some kind of really stupid linkages, which just will have only straight line realizations, where of course the reflection doesn't do anything if you have a straight line realization. Apart from really stupid ones, there will be always some non-trivial involution, which will be algebraic, right? Which doesn't come for free, again. There are definitely things which don't admit any involutions, okay? So again, so it's clearly real algebraic, affine, and compact. That's how I'm using the connectedness. If I was assuming it's not connected, then you can just take sort of separate pieces of the graph and just pull them apart, right? Send one to infinity and keep one in the finite size part, so realization space will clearly not be, or modular space will not be compact, okay? But connectivity ensures that this thing is compact, okay? Why is it real algebraic? Because it's clear that this condition is an algebraic equation of the second degree, right? We're just preserving the distance, okay? So again, the equation will be, x minus y square is equal to some constant square, right? Second order polynomial equation. And again, the expectation is that, the naive expectation is that, again, this is the naive idea of universality, is that beyond this kind of obvious restriction, there should be no other restrictions, okay? Apart from, of course, this involution, okay? And that's sort of what the theorem is, except it's not quite. So let me state this. Well, it was published in 2002, but it was proven like 4 years before that. So here's the theorem. So let X be a compact real algebraic set. When I say real algebraic, I just mean affine set. So just have a real affine space and just solution set of some polynomial equations. Okay. Then there exists L. L is one of our linkages, this mechanical linkage. Again, this is like a computer. Again, by the way, so this is a computer that engineers can realize as a computer, right? It's a bar and row and rod mechanism. It's one of the sort of basic mechanisms, whatever it's called, bar and some. Again, there is a technical bar and joint mechanism. Okay, that's how digital computer, not digital, analog computers looked like for a long time. Okay. So then there exists L as above, and so I will draw a picture. So we have this M of L moduli space, right? We'd like to say it's kind of isomorphic, right, to this X. Well, we know it cannot be literally isomorphic because of this involution business, right? So we'd expect something like a two-fold covering, maybe. Okay. And it sort of is. So there is a map, P, which is polynomial. It's trivial Z2 to some power n covering in Nash sense. And I will explain what it is, Nash sense. Okay, this stands for the group of deck transformations. So it's just a group of covering transformations of this trivial covering. Again, if you ignore this Nash business, it's really this M of L is really a disjoint union of copies of X, which are permuted by this group. It's just some, I will explain where it's coming from. This is, again, I would like this to be 2 or 1, but it's 1 billion. Again, it depends on the linkage. The more complicated the linkage is, the higher n is. That's the, again, that's all what we are getting from this theorem. Again, you would like to say something better than this, but you don't quite get the right theorem on the nose. Again, you should think of the picture that here is X, this is X, and these are just copies of X, disjoint copies of X, and there is this is our M, moduli space. These copies are permuted by this abelian group acting freely and polynomial by polynomial automorphisms of this real algebraic set. So again, it's a trivial covering in the topological sense. Let me explain what Nash is. Topological covering would mean that there are sections, right? You would like to have sections from here to various copies of X here, right? Well, I would like to say they're polynomial. They're not in this theorem. They're Nash maps. Maps, well, what they are, well, they just sort of, well, polynomial maps are defined by polynomials. This is defined by algebraic, algebraic functions. So you allow inverses to polynomials. Okay. So it's nicely invertible, so it's smooth and so on in appropriate sense, but yeah, the inverse maps to the copies. So again, you have a bunch of maps from here to here, here to here, and so on. Again, the first one is important. The rest, the deck group will take care of. Okay, but the inverse is only algebraic. It's like square root of X or something like this. It's allowed. Okay, that's the Nash. So they're kind of Nash isomorphic. So one direction is polynomial, but the opposite direction is only algebraic. Yeah, I will explain where they're coming from. And these are the guys which I would like to get rid of. It's clear from this setup is that I have to have at least one involution, right? But why do I have 1 billion of involutions? That's kind of a mystery, and I don't know how to get rid of them. I will explain where they're coming from. Okay.
What's the role of the group?
Well, it's the same role as in the previous theorem. It's just to fix coordinates somehow. You say, okay, how do you divide by a group? You say, okay, this particular node will go to the origin. And this takes care of translations. And then, you have maybe an edge. Getting rid of rotation says, well, this edge goes to this segment on the positive real line. Okay. So this is how you get rid, again, you just want to get rid of this Euclidean transformations. Okay. It's a normalization, a choice of a basis, if you like. Okay. Choice of coordinates. Because in the end, again, you just define these basic machines which do computations in coordinates, right? So you have to somehow, with all these proofs, you have to introduce coordinates one way or the other. So let me explain where symmetries are coming from, because this is the most annoying part of this theorem, of course. Okay. So I'll explain this in the context of this most famous machine, namely Passelier inversor, which, again, at least in our proof, we use it repeatedly. But again, other proofs, as far as I know, again, there are similar issues. So again, it's kind of will be most apparent in the case of Passelier inversor. So example, so inversor. So Passelier and Lipkin. There is a strange story about this. So Peselier published his paper in 1863 or 64, let's say 63. And Lipkin published his paper in 1871. So what happened with this paper is there are two papers where he kind of explains very clearly what the problem is, talks about how important it is, says that he solved it, but doesn't describe the solution.
Didn't put on the page.
I have a theory. He was a French Navy officer, and his stuff probably was classified by French Navy because it was considered to be an important engineering kind of advance, so they did not want to share it with kind of others. But then Lipkin, who was Chebyshev's student, he published his paper in actually French journal, in the journal of some kind of metallurgy and God knows what else. Like, I forgot the name of it, but it's kind of a science journal at the time, where he described the and then shortly after this paper, Peselier published identical solutions. So my theory is that, again, the solution is kind of absolutely easy. They probably come up independently with the same solution. That's the answer. But then Kempe shortly thereafter described a different solution. So let me describe the inversor. So here is the origin. And this is supposed to be a rhombus. Again, all these four sides are equal. And this is supposed to be equal sides as well. Let's say, just for normalization, these are unit sides. Okay. And then if this is point z in the complex plane, now this point is the inversion, it's 1 over z bar, okay, in complex coordinates. So this is the inversor. Well, it doesn't quite work, actually. Why? For example, you can, again, in this realization, it's clear. It's just elementary geometry. At this point and this are related by inversion, right? But what if you take this half of the rhombus and you flip it over here? Well, you get nonsense, right? Okay, because again, the realization of this might not be a rhombus, might be kind of a folded square, right? It might be something like this, right? Instead of a rhombus. That's one issue which you have to worry about. Well, that issue is easy to fix. You just introduce sort of midpoints. You drill holes in these edges. Well, there is a better way to do it mathematically, but physically, you literally drill holes. And you connect them by parallel bar, and this prevents the folding. Okay, that's easy. But then there are other problems. Here is another problem. What happens if these two vertices merge? Okay, what might happen is that you will have something which looks like this. All right, so again, this is still the origin. So these two vertices merge. So this is supposed to be z. This is supposed to be 1 over z bar. This clearly doesn't work. This point is not going to be 1 over z bar, going to be something else. Okay, there is a secondary problem on the top of it, so which one also has to deal with. But that's not where the symmetries are coming from. Symmetries are coming from something much more basic. Again, this is our input, this is our output. Remember that we are talking about the analog computers. So this is input, this is output vertex, okay? Describing some function, namely inversion. Namely, you can swap this and this. There is a symmetry here, right? There is a Z2 symmetry which interchanges this and this without affecting at all the location of the input and output, okay? So, and then if you use this guy 100 times, you have, Z2 to the 100 symmetries, okay? Then there are other machines where you again see, again, we use several of them, but again, in all the constructions I know, at some point you see symmetries, which cause this sort of Z2 to some power. Here is another machine. Again, this is the inversor. How does it really help us?
What is the result of Peselier or Lipkin?
There is a machine which converts, which describes, from our viewpoint, it's a functional linkage for the inversion in the complex plane. Okay, that's all, right? But again, in our paper, we use it repeatedly. Again, I will not have time to talk about how we use it. But the point is, it's a very simple machine, which is easy to analyze. If you want to do a clean algebra geometric analysis, which of course, Kempe did not even know, didn't have even the language to state this. He was talking about drawing a curve in the plane, that's all. But again, if you want to do a clean analysis, you have to reduce it to simple machines and then have some kind of fiber product arguments by combining them. So that's why we like this. So again, we managed to fix it. Okay, there are ways to prevent all these degenerations. By the way, engineers knew about this, but they didn't mind somehow because they didn't consider it to be practical anyhow. Okay. So here is another machine. How do you kind of add numbers? Again, it's supposed to be a parallelogram or a rhombus. Again, they're supposed to be midpoints. So supposed to be this supposed to be the same as this, supposed to be the same as this. Okay, so maybe this is, say, Z, this is W. Then what is this? Well, this is Z plus W divided by 2. This is how you almost add numbers, except you have to divide, okay? And this is free floating. There's no anchor here. But you can use the same machine to multiply by 2, right? You have to plug this at the origin, make this as input, and this will be twice the input, right? Again, the same machine describes multiplication by 2. Right? If this is the origin, if this is Z, then this will be twice Z, okay? So this gets rid of the factor of 2, okay? So where is the symmetry here? Well, you can flip this, right? Flip this, again, there is a line of reflection. You can flip it to the other side. That's a symmetry, which doesn't affect at all the input and output, okay? And the same here, the same reflection symmetry. Again, there is the issue with parallelogram, but again, there is a way to make it rigid by introducing extra bars. So again, this is fixable, but the symmetries we just don't know how to get rid of. They're kind of everywhere. On every step of the construction, you have symmetries. And again, so this allows you to do the addition, right? You first do addition, except you divide by 2, and then you multiply by 2. So the result, when you combine the two machines, you get the addition. And then there is a trick how to do multiplication. The point is that if you know how to do addition and inversion, you can do multiplication as well. So there is a trick which reduces multiplication to inversion. But in any case, that's just arithmetic, high school arithmetic. But now you see where symmetries are coming from, right? They're coming from symmetries of realizations which don't affect at all the inputs and outputs, right? And we don't know how to get rid of them. Now let me explain the relation between Lipkin and between the Kempe and von Staudt, okay? And that explained in our paper, which almost nobody read, I think. It's published in some proceedings for Jean-Luc Berlinski. Algebraic geometers just did not care about this, and nobody else did. So let me explain how to go from arrangements. Sorry? Yeah, progress in mathematics, right. From arrangements to, you did, okay, good, so somebody did. So. To linkages. Does anybody besides you know how to do it? No, okay, so you know this, okay. No, but you can figure it out by yourself. Okay, so let me explain how to do it. So let's think about this points and lines. So there are points and lines, right, in the projective geometry. So let's think about the real projective plane now. And real projective plane is covered by the two spheres, right? So you'll think of the two-dimensional sphere. And how do I lift? Well, this line, of course, will lift to a geodesic circle on the sphere, right? Or alternatively, so I will just still call it L, even though it's technically speaking a two-fold cover of this line, right? And this point, P, will lift to 2 points, P twiddle and minus P twiddle on this line, right? Now you already see the Z2 symmetry. There's ambiguity. Once you go to Euclidean space, you immediately see this Z2 symmetries present here, because you can lift to this point, you can lift to this point, you still have the same incidence, right? And now how do I get a linkage? Well, I replace this line by L perp, by the dual point, except that there is a +1 and there is -1. And again, you have ambiguity in which one to choose, right? And now what's the linkage condition is that the distance, spherical distance between this and this is pi/2, right? That encodes the incidence condition, right? Just the condition at the length of a segment on the sphere is pi/2, okay? If you want to really make it Euclidean linkage, you should go to Euclidean 3 space, right? Just add extra origin here and, then just draw these guys. It's okay. Again, once you go to the sphere, I can do it in Euclidean space as well. So this means one can kind of prove Kempe using von Staudt, except that you have to pay the price. Again, these Z2 symmetries just show up out of nowhere. We got rid of them because they were not present in von Staudt's theorem, right? There were no Z2 symmetries. But here, once you go to Euclidean geometry, just somehow rediscover them. They're again there, okay? And there is a small disadvantage is that Kempe von Staudt works over integers or rationals, and so there is a little drawback here. So you don't get arbitrary variety, but only defined over integers or rational numbers. But again, that's a minor drawback. But that's the relation between two constructions, right? So you can kind of do some version of Kempe's theorem using von Staudt. Okay. And again, Kempe could have realized this, of course, but he probably didn't care. Okay. Okay, so, and I'm out of time, so I have to stop here. And tomorrow I will explain how to relate to Coxeter groups and three manifold groups. How to relate all this stuff to three-dimensional topology.